Now, we are going to talk about continuity on an interval. Before we discuss intervals, we first need two ideas: continuity from the right and continuity from the left. A function is continuous from the right at a if the right-hand limit equals the function value. This means that when x gets close to a from the right side, the function values get closer and closer to f of a. A function is continuous from the left at a if the left-hand limit equals the function value. This means when x approaches a from the left side, the function values approach f of a. These ideas are useful when we work with endpoints of intervals, because sometimes we can only approach a point from one side. Now, let's look at an example. We want to find the interval where the function is continuous. First, we need to find the domain of the function. F of x equals square root of x plus 3. This is a square root. The expression inside the square root must be greater than or equal to 0. So we are going to let x plus 3 greater than or equal to 0. And we need to solve for x from here. So I'm going to subtract 3 from both sides. So f of x is defined if x is greater than or equal to negative 3. This is my domain. Here is the domain in interval notation. I use square bracket here because negative 3 is included. Now, let's identify the continuous interval. Square root functions are continuous whenever they are defined. Since f of x is defined from negative 3 to infinity, so the function is continuous for all x that is greater than negative 3. Notice that I used parentheses at negative 3 because we only know the function is continuous for x greater than negative 3. We are not sure yet if it is continuous at x equals negative 3. So we need to check the endpoint. If it is continuous there, then we will include negative 3 in the interval. Now, we check the endpoint x equals negative 3. Since the interval starts at negative 3, we have no values to the left of negative 3 in the domain. So we only check the right-hand limit. This is the notation of the right-hand limit. This little plus sign indicating that x is approaching negative 3 from the right. Now, I am replacing x with negative 3. Negative 3 plus 3 is 0, and square root of 0 is also 0. So the right-hand limit of the function equals 0. Now, let's compute the function value at x equals negative 3. Since f of x is the square root of x plus 3, to find f of negative 3, I'll replace x with negative 3. Negative 3 plus 3 is 0, and square root of 0 is also 0. Now, let's compare the right-hand limit and the function value at x equals negative 3. the right-hand limit of the function equals 0, and the function value at x equals -3 is also 0. Are they equal? Since the right-hand limit of the function equals the function value at x equals -3, the function is continuous from the right at x equals -3. Therefore, we include -3 in the interval of continuity. The key idea is this: a function is continuous everywhere in its domain. So first, find the domain, and that tells you where the function is continuous. Now, let's look at another important result called the composite function theorem. This theorem helps us evaluate limits when one function is inside another function. The theorem says the following: if f of x is continuous at L and limit of g of x as x approaches a equals L, then the limit of f of g of x as x approaches a equals f of the limit of g of x as x approaches a, which is f of L. In simple terms, if the outer function is continuous, we can plug the limit inside the function. Now, let's look at an example. We want to evaluate the limit of sine of x minus pi as x approaches pi. First, look at the expression inside the sine function, which is x minus pi. As x approaches pi, the expression x minus pi approaches 0. Since sine is continuous, we can plug this limit directly in the sine function. So we have sine of limit of x minus pi as x approaches pi. Now let's evaluate the limit. We will substitute x with pi. Pi minus pi is 0. So the limit of x minus pi as x approaches pi is 0. Now I have sine of 0, and sine of 0 is 0. So the limit of sine of x minus pi as x approaches pi is 0. Now let's talk about another very important theorem called the Intermediate Value Theorem. The theorem says, let f be continuous over a closed bounded interval from a to b. If z is any number between f of a and f of b, then there is a number c in between a and b, satisfying f of c equals z. Let's look at this graph. This is my function f, and it's continuous. This is the interval from a to b. At x equals a, the corresponding y value is f of a. At x equals b, the corresponding y value is f of b. If z is the number in between f of a and f of b, then there is a number c in between a and b, satisfying that f of c is equal to z. In simple words, if a function is continuous and you move from x equals a to x equals b, the graph cannot skip any values in between. it must pass through every value between f of A and f of B. So if we choose a number z between those two values, the graph must cross that value at some point. And that point happens at some number c in between A and B. At that point, we have f of c equals z. The intermediate value theorem is very useful because it tells us that a solution must exist, even if we do not know exactly where it is.